Yeah. So last class, towards the end of last class, we have seen the motivation for studying MOSFET, which is a switch, electronic switch, and MOSFET has a basic, part as this MOS metal oxide semiconductor junction. So with this metal oxide semiconductor junction, they make this metal oxide semiconductor field effect transistor. That's what we have seen. So this lecture, we will begin with the discussion of MOSFET, MOS junction. All right. So, so metal oxide semiconductor junction, call it MOS junction or MOSCAP. MOSCAP, I already discussed, it is like a capacitor. So that's the reason we call it MOSCAP. Because after all, the field effect transistor is basically the capacitive effect. So as it's a capacitor, our goal is to derive CV characteristics of the MOSCAP. So once we understand the CV characteristics, then when we make MOSFET, so we will understand CV as well as IV also. So because the CV characteristics can be derived only from the charge picture inside the junction, and only the charge is what is going to travel. So charge picture is important. In other words, CV characteristics is the final goal when we talk about MOS junction. So what do we mean by CV characteristics? So this is the MOS junction. We have MOS, and then you apply a battery, and then the battery voltage, say you slowly vary, and at every voltage point, there is actually a sinusoidal on top of this V. So this is basically the operating point, on top of which you have a sinusoidal, because after all, there is no DC current that is going to flow. So CV here definitely means based on this AC small signal source. So you bias this MOS junction at different voltages, and at every voltage you apply a small sinusoidal and then see what is the current, and accordingly you decide what is the capacitance. So if you see the capacitance curve, how it looks. So we have normalized the capacitance of the MOS junction with respect to Cox. We will come to this little later after seeing this figure. And on the right axis, on the x-axis, we have voltage. So at every voltage, you apply sinusoidal and see what is the capacitance. So if you see, it is not going to be a constant like how you find for a parallel plate capacitor. So it is varying with the bias point. So there is one red curve here, okay, which is at frequency like 1 kilohertz. And then if you change frequency, the curve is changing to the in the right side portion, not in the left side portion. And if you decrease the frequency further, if you see that it is still changing. I mean, the curve is you are getting different curves for different frequencies. And then there are some special features of the CV curve, something noted like VFB and VT we will see later. And if you see the voltages range, this is how it is. Okay, so this is kind of very old MOSFET, you can say. Very new MOSFET, this voltage axis will be scaled. So what is this Cox? Cox is the oxide capacitance. So that is, just take this oxide, only oxide, and if you put two electrodes either side of the oxide, then the capacitance of this oxide layer, it's called sometimes oxide layer, that is Cox. Because it is an insulator, so definitely you can have a capacitor made out of that insulator if you just put two electrodes on either side. And that is the capacitance of the semi oxide, Cox. And to obtain CV characteristics, we need to study the charge picture in the junction as a function of voltage. As I've seen, voltage is the operating point. So we need to study the charge picture at different voltages. So as a function of voltage, you should find the charge picture also. So before we move on to charge picture, we should first understand the device structure a little more in detail. So that is this device structure. So MOS. So in our discussion, we will consider p-type substrate. So in all our discussions, even in MOS junction or MOSFET, we will consider p-type substrate. Substrate is this. Why I am calling this substrate? Because that is what is used on top of which the substrate is like the bottom, which is like substratum, in the sense the base. Okay, so on top of which you grow oxide, and on top of that you deposit metal. So that is the reason the semiconductor portion is sometimes referred to as substrate. Okay, so p-type semiconductor or p-type substrate we call it. And it's sometimes called as body also. So that is one thing, and you have to extend the logic or the concept to n-type semiconductor, because we might ask them in the tutorial or in the exam. So we consider p-type semiconductor. The metal is also called gate. So like we call this p-type as substrate or body, the metal also is called gate. Okay, generally this gate is different from the gate that you have in digital circuits. Okay, don't get confused, but maybe possibly that digital logic gate has come from this itself. So this is like gate, you know, it's like opening, in the sense that is what is the thing that controls flow. So generally gate can be metal or heavily doped semiconductor. That is, the gate is a different material than substrate. Normally gate is a different material than substrate. It can be metal, we just retain metal, but sometimes it can be even polysilicon also. Okay, so even then we just the name doesn't change, we still call it MOS or MOSFET. So if the substrate is silicon, gate can be heavily doped polysilicon. Because why it is heavily doped? Because you want to mimic a metallic behavior, so it should be heavily doped. So S is p-type silicon, most of our discussion. So O for oxide, if it is silicon, then it will be silicon dioxide. All right, so this is what I have said just now. So regarding the interface, now the structure is done. MOS, what can be M and what is O and what is S, we have seen. So now that there is this interface O and S, oxide and silicon. So there is this interface which is very crucial. It plays a significant role or in device characteristics, IV or CV. Okay, so and it is it is of somewhat great complexity, so we'll not get into too much of details of this interface, but the crucial points are as follows. So there will be some charges in the oxide also, so there will be some charge at the interface, and there will be some charge in the oxide. Okay, so uncompensated charge or something of that sort, you can say, but uncompensated at the same place. Okay, so it like okay, we'll come to that later. So so there are four types of charges. QF is called fixed charge at the interface. So there is a fixed amount of charge which doesn't change with bias. That is the reason it is called fixed. So fixed charge doesn't change with bias, and that is found in the oxide semiconductor interface. Okay, that why that comes is because of the stoichiometry and the reaction between semiconductor and oxide. So when oxide is grown. So QIT, I and T stand for interface and trapped. So interface trapped charges. So there will be some trapped charges here, and the trapping of charges depends on actually bias. So that is bias dependent charge, which is somewhat more complex than QF. And QOT, this oxide trapped charge. Similar, so the first two are related to interface charges. Interface. So first is fixed charge at the interface, and second is variable charge, you can say, that is called interface trapped charge. The next two are actually inside oxide, not at the interface. And QOT means oxide trapped charge, and QM means M for mobile charge. So some ions can be there. They might have got trapped during processing, silicon processing, wafer processing. So they can move depending on bias. Okay, so some ions can be there, so which can be moving. So those are mobile charges. Similar to interface, you can have trapped charges inside oxide also, which depend on bias. So for simplicity in this course, we will consider only QF. All right. So that is fixed charge at the interface, which is bias independent. So this is what is our familiar structure P and N, and when you join P and N like this, there is charge transfer across the junction. Okay, why is there a charge transfer across the junction? P and N, they are side by side. There is a concentration gradient, hole and electron, and in equilibrium the Fermi level has to align. So there is charge transfer, and you see a depletion region, etc., in the equilibrium. If you have a MOS junction like this, okay, so if you just have a MOS MOS, that's all. Will there be charge transfer in this case across the MOS junction? Will there be any charge transfer? Can somebody answer?
Yes, sir.
Yes, sir.
Yes.
So how will the charge transfer? Through? It has to transfer through what? If it is transferring?
Diffusion and drift, sir.
Drift. Why? There is no field, no? We are not applying any field.
Then it should be a diffusion, sir.
Okay, but diffusing from where to where? From metal to semiconductor or semiconductor to metal? So that should happen through what?
Displacement current.
Okay, displacement current. Okay. So why displacement?
It is similar to that of a capacitor.
Yeah, similar to that of a capacitor. So the displacement current and all you can say when I apply bias. So think of this analogy. I have metal and it is separated, and a semiconductor. They are separated by just vacuum or oxide. I'm not saying it is any bias or anything. Just remember, just P and N junction. Here MOS, and here I have a metal separated by some distance, vacuum or air. Actually, vacuum or air, you can say. Okay, so you have a semiconductor. So will there be any charge transfer? So what you are saying is, if I hold metal in my left hand and if I hold semiconductor in my right hand, charge transfer will happen automatically. Okay, is that what you are saying? Is it possible? Tell me yes or no. At least that much you should think and tell, no?
No, sir.
Yeah, how is it possible? Then all over the all our surroundings, the charge simply gets transferred, just like that. No, there is some barrier. So vacuum means what? It is like charge has to come out of semiconductor and be present in vacuum. For that you need work function difference and all that. You cannot simply pull electron out of semiconductor just like that. No matter what you have surrounding, say there is a metal, even if it has lesser concentration or of electrons or more concentration of electron, doesn't mean they will simply come out of metal and to the vacuum, right? So for that, for electrons to come out of metal, you need work function. Okay. So and then you put inside semiconductor that releases some energy. That is fine. But how can you first get electron out of metal into vacuum? That's not possible. So if you cannot have this kind of charge transfer happening, if you hold metal in left hand, semiconductor in right hand, how can you expect charge transfer to happen just because you have some solid in between? MOS. O is also insulator. Vacuum also is insulator. Fine. If from metal to oxide, to take electron from metal into oxide, you don't need that much energy as you need in case of metal to vacuum. That is fine, because oxide also will have, insulator also has some conduction band, but very high above. So very close to UE0, you can say, vacuum level. So you may not need this much energy as you require to take an electron out of metal into vacuum or air. You will not need that much of energy to take electron out of metal to oxide. But how will that energy also come? It is not possible. So simply, you cannot have charge transfer just because you have MOS. Okay, doesn't mean anything. I mean, you still the metal and semiconductor can be treated as still separate. Then what is the meaning of charge picture? All that. So just as M and S separated by vacuum means that we have not formed any junction. Similarly, just M and S, metal and semiconductor, separated by an oxide does not mean we have formed an MOS junction, because they are not interacting at all, metal and semiconductor. Then when do we say an MOS junction is formed? So we have to say, so this is the MOS junction. So when we say there should be some talking between M and S, and also if I'll just draw it here, if you just have MOS like this, you will simply put battery or something. That is one way of saying there will be connection. So I will not have battery. Okay. So when I talk about MOS junction, I'll talk about it only when I apply bias, you might say. So they may not interact just if you have MOS, but when I have a battery, then there can be some interaction, you can say. Then first to understand how it behaves, you should first also see how it behaves at zero bias. So doesn't mean I'll just keep this open like this. So I have to make it zero bias. So that is equilibrium. I have to bring equilibrium picture. Okay. So I can obtain equilibrium picture only by connecting M and S. So that is what is zero bias. Okay. And which is equilibrium. So to connect MOS like this, I need some metal, okay, which connects this M and which connects this S on left and right hand sides. So instead of choosing a different material, a different metal, I'll choose the same M, because if I choose a different material, then I have to talk about contact potential between that material and this metal and semiconductor, etc. So since I have a metal here, I just take the same metal and then connect it to the right hand side, and I am showing it as a bigger metal, another contact with the semiconductor junction. This is what is forming a MOS junction under equilibrium. Okay, you have to bring in equilibrium here, right? So that is zero bias. So this way an MOS junction is formed, and in addition we see and in that process what we are seeing is an additional junction that is coming up, which is metal semiconductor junction, which we have seen in the previous class. Okay, so with this cannot be avoided. Now we can break the metal wire and insert a battery to study the properties of the MOS junction. Okay, so now what we do is just break the metal wire and then put a battery to study, and then say voltage is 0 or voltage is positive, voltage is negative, and then study the charge picture. Okay, so there are two junctions here. One is MOS junction, another is SM junction, that is metal semiconductor junction. So for simplicity, we will first consider ideal MOS junction. Okay, so seems there are more junctions. It's not just MOS junction. We have this SM junction also. So let us start with discussing some ideal MOS junction. What it means. Is it clear so far? Yes or no?
Yes.
Yeah. So ideal MOS junction. So an ideal MOS junction means what? No charge in the device for applied voltage of 0. So that's what we expect of a capacitor, right? So a capacitor, if you just take, you don't want to have a automatic somewhere some charge will be there inside. Then if you apply voltage and then try to relate voltage and charge inside the device, then you cannot say constant just Q equal to CV, because there will be some already there will be some charge that was there even before. Okay, even with zero bias. So then it will be Q equal to CV plus some Q naught. So we don't want such things here. So so basically ideal MOS junction means what? Just like any normal capacitor which doesn't have any charge for zero applied voltage. So you should not have any charge in the device for zero applied voltage. So it requires two things. So ideal MOS junction means two things have to satisfy. So phi ms equal to 0. We have seen this phi ms what it means in the previous class in the discussion of Schottky junction. All right, so just a recap. So what is phi ms? It is the contact potential between a metal semiconductor junction. Okay, and the sign of phi ms is something like this. Plus the reference is, when you say phi ms is the contact potential, always the reference is with respect to with respect means in the sense positive on the semiconductor side, negative on the metal side. So I have discussed this. So this is the way you talk. How you say in PN junction, it is V built in. But what is the sign of V built in? Which side is positive? Which side is negative? So you always remember, right? It is N type, N side positive, P side it will be negative. Where VBI is always positive here. Whereas in our case, phi ms can be negative also. Okay, but reference is like this. So semiconductor is positive and metal side it is negative, and the contact potential is phi ms. Here phi ms can be greater than or less than 0. Phi ms can be greater than or less than 0 depending on the Fermi levels between semiconductor and metal. Okay, so we don't know what is the value of phi ms, but just that the reference is something like this, plus and minus on this way. And what is phi ms? So phi m minus phi s, metal Fermi level minus semiconductor Fermi level by Q. Difference between the Fermi levels by Q. Difference between work functions. So indirectly difference between the Fermi levels. And if phi ms is equal to 0, which means metal Fermi level aligns with semiconductor Fermi level. So which is the case of no charge transfer across metal semiconductor junction under equilibrium. So why we now you will understand why we are saying for ideal MOS junction you should have phi ms equal to 0, because if only when phi ms is 0, then metal and semiconductor Fermi levels align each other, in which case there will be no charge transfer, because Fermi level aligns means no charge transfer. Okay, so it is not like aligning after charge transfer. I'm saying just when you form the junction itself, Fermi levels on both sides are seen to be same, so there need not be further charge transfer. So if there is no charge transfer, there is no built-in field, there is no potential difference across the junction. If you draw band diagram, it will just simply look like this. So both sides Fermi levels match even before and after. So this is E naught vacuum level. So EC, EF, EV. So clearly you can see that no band bending. There is no band bending, because band bending is what gives you charge, right? We have seen in PN junction. So there is no band bending, no charge in semiconductor. All right. So what is the implication of phi ms equal to 0 then? So if you apply V equal to 0 like this and try to draw band diagram. So MOSM, what you should draw first? Fermi levels you should align. So this is the Fermi level EF. S and M, ideal phi ms equal to 0. So they are aligning beforehand. All right. So V equal to 0. So which means what? The left, this is the same metal. Okay, same metal. So their Fermi levels should align if you don't have this V at all. So, but if you have some positive or negative V, then the Fermi level difference between this left side M and right side M will be Q times V. But now that V equal to 0 and it is the same metal, the Fermi level on the left side metal should align with the Fermi level on the right side metal. So that is what I have drawn here. Okay, so semiconductor metal Fermi level aligns because phi ms equal to 0, and left hand side, right hand side, same metal Fermi level aligns, not because it is just same metal, but because V is 0. Okay, V is 0, and if V is there, if you apply some V 0, I mean greater than 0 or less than 0, this EF difference will be according to the applied voltage, EF on left and right. And E naught is constant throughout. Okay, so and see, I am not drawing EC EV of the oxide. You can draw, we will come to that later. E naught I am drawing for now. Okay, not like we cannot draw band diagram here, or we shouldn't. We should actually draw, but for now we are not drawing. But if you want to draw, it will be like this will be the EC of oxide, and somewhere down, so much bigger energy gap, right? So this is the energy gap of semiconductor. This is the energy gap of silicon. All right, oxide, which is very large, though diagram is not to scale. So no band bending in semiconductor. So there is no band bending at the semiconductor metal junction. We have seen, in the previous page. But now in this MOS junction also there is no band bending, because the same Fermi level, is flat, and this side also it is flat. So just extending EC just the same way, straight line. So there is no band bending throughout in the semiconductor, implies no charge in semiconductor. No charge in metal also. When there is no charge in semiconductor, there is no charge in metal. So that is the implication of phi ms equal to 0. So not just in this metal semiconductor junction. Why we are drawing this is, it is not just that this semiconductor metal junction there is no charge because phi ms is 0. But if you put V equal to 0 and connect this way, this MOS junction, even here also the charge is 0. So that's what we wanted to say there. And then next thing that is required is interface charge QF equal to 0. So if QF is not equal, then there must be compensating charge in the device somewhere, so that the device overall is neutral. You cannot have some MOS junction, you fabricate the device and then say that okay, there is already some charge inside. So it will somehow attract negative charge and then it will compensate even during the process or wafer processing. So you cannot have a charged device or something like that just out of fab. So it will be somewhere that neutralization will happen, in the sense if QF is there at the interface, then that is positive, say this QF is positive charge, then somewhere negative charge will be there, so that this positive charge, negative charge cancels and the device is neutral overall. Okay. So clearly, when in the definition of ideal MOS junction, no charge in the device means not actually no net charge. Net charge will anyway be in the device be zero. Okay, but there is no plus charge minus charge separation. That's what we want to say here. I didn't say that earlier because that may cause confusion or lack of understanding, but now I'm telling with some actually familiarity. So it is not that net charge is zero, net charge will be going to be zero. Ideal junction means there is not even charge separation. Okay, so QF has to be zero. So it implies that this QF charge will create offset in our CV characteristics. So there is already some plus Q and then there is minus Q. They are separated by some distance, because if minus Q is sitting on plus Q, then we can treat it like there is no charge at all, right? But it cannot happen because QF is at the interface and negative charge will be somewhat distributed. Okay, that is going to compensate QF. So there is some charge separation, which means whenever there is some charge separation between plus and negative charge, then there is a capacitance associated with that positive and negative charge. So if you draw CV characteristics, then there will be some offset, so which we don't want for an ideal junction. So ideal MOSCAP implies no charge in the device, requires phi ms equal to 0 and QF equal to 0. So with this, is this clear so far? Yes or no? Yes or no?
Sir.
So now coming to analysis of ideal MOSCAP. So first let us start with V equal to 0 we have seen already. So there is no charge in the device. That is the definition of ideal MOSCAP. So we have seen how charge is not there for V equal to 0. Then we have to see for V less than 0. All right. So this is the biasing MOSM. So V less than 0. Now what's the current at steady state? Say now you switched on or something. You say you observe steady state. Okay, I have not shown the switch or anything, but I've just written as steady state. So the current through the device is what? Can somebody answer? Answer is there. Okay, so what is the current at steady state? It is 0. Why? Because there is oxide insulator in between. So how can you have any current? So it is not possible. There is some insulator in between. So you cannot have any current like this, even if V is not 0. So 0 current implies the MOSCAP is always under equilibrium, even under applied bias. This is something very strange, right? So far in the definition of equilibrium, we have said that there should not be any external excitation other than temperature. Even if temperature gradient is there, then it is not in equilibrium. And no other external excitation other than temperature means even voltage also should not be there. So, but that definition we are trying to kind of overwrite here. It is correct only. Why? Because see, it is not like the excitation is from light or something or any of that sort. So it is voltage excitation, but there is no net movement of charge. There is no net movement of energy, which is the definition we have seen, right? So why there is no net movement of charge? So after all, this is insulator. So when you have V less than 0, some transient will be there, and after the transient, things are like as they are. Like there is no further movement of electrons, further movement of holes, nothing. So movement is stopped. So that picture is equilibrium. Okay, so there is no net flow of carriers. So that's why it is equilibrium. So MOSCAP is always under equilibrium, even under applied bias. Now the thing is, how much of the applied voltage drops across MOS junction and the right side SM junction. So now that you have applied voltage, how does it distribute over all these different regions, MOS, M, etc. Since MOS junction is in equilibrium, the SM junction also should be in equilibrium because there is no current, right? So if there is no current in the MOS junction because there is an oxide, there cannot be any current in the semiconductor metal junction also, right? So if there should not be any current in the SM junction, then SM junction also should be in equilibrium. So which means what? There should not be any additional drop other than the equilibrium contact potential. Okay. So because we know that any junction, if it is in equilibrium, then there is a contact potential, and current will flow through the junction only if you apply bias or something, which disturbs the potential drop across the barrier. Okay, so it will be different from contact potential, which is what we have seen in the PN junction. So there should not be any additional drop other than the equilibrium contact potential. Here in this case, 0, because we have considered ideal MOSCAP. So 5ms is 0, so contact potential is 0. Okay, so even if it is non-zero, you cannot have any additional drop other than 5ms, because just because you have applied bias, because if the potential difference is not 5ms, then there has to be some current flow between S and M, which violates the equilibrium picture or the zero current case, zero current requirement. So that's what it is. So therefore, entire voltage drop, entire applied voltage drops across the MOS junction. Still, it's in equilibrium because no current can flow through MOS junction. So entire voltage applied across drops across MOS junction. And let us see what we have here. So for V less than 0, there should be negative charge on the metal, and there should be positive charge on the semiconductor, which is p-type. After all, V less than 0 means this side negative, so negative charge should be there on the metal, and positive charge should be in the semiconductor, because entire voltage drop happens here. It's not like positive charge will be on this metal. No. What does it? There is no meaning of saying a positive charge will be on this metal, because metal and semiconductor charge can transfer. Okay, so it is not here. It has to stop here. The negative charge should come and stop here because it cannot cross this oxide. Okay, whereas the positive charge that is supplied by the battery this way, okay, it will not stop here because metal and semiconductor, it can move. Okay, and then it can come and stay here, and it cannot stay, it cannot go beyond this surface because there is oxide. So you will have charges here and here. Okay, charges location. So you can have it have the charge here, negative charge, it comes and sits here because it cannot cross oxide, and the positive charge comes and sits here, it cannot cross the oxide further. So positive charge in semiconductor, how does it come? So this is a p-type semiconductor. Okay, so this is a p-type semiconductor. Positive charge can come from holes only, because electrons are negative charge, and p-type means the dopant concentration is acceptor concentration, which is Na minus. So positive charge means it can only come from holes. So hole concentration has to increase near the surface. That is the only way you can have positive charge here. Okay, so this is from here onwards we'll draw a lot of curves, just pay attention. So hole concentration, because positive charge should come here, positive charge in semiconductor can only, p-type semiconductor can only come from holes. So hole concentration has to go up here. That's how positive charge can come. If hole concentration is increasing towards the surface, then electron concentration should be decreasing towards the surface. Why? Because that is P is increasing implies N is decreasing, because Pn is equal to Ni square. Why? Because MOS junction is in equilibrium. Okay, so even under applied bias, MOS junction is in equilibrium, so Pn is equal to Ni square. So if P is increasing, N is decreasing, such that Pn is Ni square. So if you see, it is still in equilibrium because drift and diffusion cancel each other. So why? Because the drift diffusion will be in this direction for the holes. So say there is a hole here, say hole diffusion will be in this direction, and I mean, I'm writing this arrow, but don't think it will go inside oxide. Okay, maybe I'll not write. I mean, it may confuse. So drift will be in this direction. Why? We will see that shortly when we draw electric field. Okay, so for now, just take it that different diffusion cancel each other in this space charge region, because there is a space charge region, because there is positive charge accumulation. So if you draw rho, which is the space charge density q times p minus n minus na as a function of x, so what you see is this way the charge will start, and it will go to some peak here, because that is what we see, right? P is pp naught somewhere deep inside, and n is np naught, which are the equilibrium concentrations. So they are getting disturbed from their equilibrium concentrations only very near to the interface. So near to the interface, you will see some very large rho, and it decays as you move into the neutral region. Okay, so this is where pp naught and np naught you will see. So that is what it is. So it is starting from very high value, and it is going to 0 by the end of neutral region, where you will have the equilibrium carrier concentrations. So on the metal side, you should have a negative charge. I am showing it as an impulse function because it is really very thin. Even in the semiconductor also, this region will be very small. I mean, this thickness is very small, which will be of the order of Debye length. Not just the Debye length. When you put Debye length, will have a doping value in the expression, right? Epsilon Vt by Q and D square root. So, but you should put actually the concentration of the majority carrier as this one, which is much larger than this. So this will be really thin, very thin region. So even the semiconductor region also, you can show it like an impulse function like this, which we show in the metal region. But for understanding sake, we have to still show like this. So now if you see electric field, so you see that electric field is given by dE by dx equal to rho by epsilon naught. All right. So rho by epsilon naught. So rho is positive here. So electric field slope should be positive, and direction should be negative, because positive to negative. So that is why I have drawn here this way. So there is positive to negative, and so there is a positive slope here because rho is positive, and it is decaying to 0 here because there is no charge beyond this space charge region. So this is neutral region, so electric field is 0. So electric field is starting like this. When charge started building up here, electric field is starting, and it is getting added because charge is getting more. It is getting added, but it is in the negative direction, so it is coming down like this, and it stays constant here because E is E-ox. So this is oxide. E-ox is constant because rho is 0 in oxide. In the oxide, you don't have any charge. All right. So when the charge inside oxide is 0, then electric field from this expression, Poisson's equation, dE by dx equal to rho by epsilon naught. Rho is 0 means slope should be 0. So E epsilon ox is constant. So this is epsilon ox, epsilon inside oxide. And then it's, because there is some impulse function here, immediately the slope should be very high. In other words, if rho is impulse, then E should be discontinuous. So in the sense, it goes to 0 all of a sudden. So, you take it to 0. Now, the piling up of majority carriers holes in this case, because p-type semiconductor at the oxide semiconductor interface is referred to as accumulation. So why is it accumulation? Accumulation is what meaning? So you have something and you keep adding to it, right? So that is what is accumulation. You are accumulating money, things like that. So you have whole is the majority carrier concentration. So you have more of majority anyway. So take the majority carrier concentration for the definition. and majority carrier concentration is increasing. So you have added holes. So you have accumulated holes near the surface. So that is why this is called accumulation of carriers, or basically majority carriers. And this this piling up of majority carriers is called accumulation. Okay, fine. Now that we have got the carrier profile, space charge distribution, what is remaining is relating electric field to charge, or actually the voltage, applied voltage to charge in the semiconductor. So charge is electric field, charge, electric field, voltage. So we have these three things. So how do we relate charge and electric field? We have Gauss's law. Electric field voltage, we have to integrate field to get voltage. Okay, so take electric field picture, which is the center thing from which we get both charge and voltage. So this is how the electric field picture is. Okay, we have just redrawn it here, and this thickness is T ox, and this value is say epsilon ox, E ox, electric field inside oxide. So what is the value? How do you relate E ox to charge? So field to charge from Gauss's law. So MOS junction you take, it is a 1D case. So things vary only in X direction. So fields are all in only one direction, that is X direction. So Y direction, Z direction fields are 0, because cross section you can treat it like infinity, and there is no variation in the YZ plane. Variation is only there in the X plane, X axis. So you have taken a Gaussian pillbox. So one surface, cylindrical surface, is inside oxide, and conventional field direction is electric field in the positive X direction. So this is the direction of field, and value is epsilon ox. And the other surface, cylindrical, this planar surface of the Gaussian cylinder, you take it in the neutral region. So in the sense, I am taking the Gaussian pillbox like this. So one surface is here, that is this. Another surface is here. Electric field is 0. There is, by then charge has become 0. So for this, if you start using Gauss's law, so integral, closed integral epsilon E, basically because epsilon is changing, right? Oxide has an epsilon, semiconductor has an epsilon. So better to use del dot D equal to rho. So in other words, integral epsilon E dot ds equal to Q enclosed. So here we have epsilon ox in this direction, positive X direction, and the area vector of this oxide, okay, so it is in negative X direction, right? So the area vector is in the negative X direction. So E ox times ds will be negative. Okay, so because the vectors are in the opposite direction, so dot product, so there's a negative sign here. Minus epsilon ox, epsilon is epsilon ox because oxide, E ox is electric field in the oxide. QS is enclosed charge in the semiconductor. Why enclosed charge in the S for semiconductor? Okay, so QS is the charge in the semiconductor. Why charge in the semiconductor? Because there is no charge in the oxide. So the two regions are there, oxide and semiconductor, and what you have to put is just semiconductor charge. That's all. So you have related electric field to charge. Now, if you want to relate the electric field to voltage, you have to integrate line integral electric field E dot dx. Metal to semiconductor means psi m minus psi s. That's what. So metal to semiconductor. So you are integrating from left x axis along positive x axis. Towards positive x axis. So towards positive x axis. So epsilon ox, T ox. So that is what it is. Epsilon ox. Though it is negative, but epsilon ox is negative. That's what we mean. So E dot dx. So epsilon ox dx equal to V. So clearly I have neglected, there is no voltage drop in metal because metal electric field dies down so fast. And we have seen earlier that, so even electric field dies very fast in the semiconductor region also. This thickness is very small, we said. So this area is also neglected compared to this big area. So clearly area under E versus X in the semiconductor is negligible. Okay, that is why we have only area of electric field in the oxide alone. Okay, so epsilon ox dx equal to V, because psi m minus psi s, potential difference between between metal and semiconductor is applied voltage V now. So epsilon ox, you would bring it from here, minus qs by epsilon ox into T ox. So qs is equal to minus C ox V. So just writing qs equal to minus, there is minus sign. So V times C ox. So the clearly C ox is this epsilon x goes that side, T ox comes down. So epsilon ox by T ox. So where C ox equal to epsilon ox by T ox is the oxide capacitance with units of farad per centimeter square. Why? Because if this is oxide, if you put two electrodes on either side and oxide thickness is T ox, the capacitance per unit area of the structure is C ox, because C ox into A is epsilon A by D, your well-known formula, right? So this is the actual full capacitance, and you multiply epsilon A and by thickness D. So this is actually the oxide capacitance. So is it clear so far?
Yes.
Yeah. So any questions? So yeah. So is there a free slot today for you? I better take a class online so that I am sure that you are just listening to me, and if I just post video, I am doubtful when you will watch and etc. Because we have only few classes left. So if there is any break, then you wouldn't understand these concepts, because we will be going at at a quicker pace. So tell me, so is there a free slot today? Sorry.